Dzień dobry, and welcome, and thank you all for joining us. So today we're going to talk about how Wix successfully dealt with its scaling challenges and how Wix used effective strategies to make sure that our 4,000 microservices run smoothly with ever-growing scale of traffic and data. My name is Natan Silnitsky, and I'm a backend infrastructure tech lead at Wix. And for the last 7 years, I've worked on all kinds of infrastructure tools for Wix's microservices, starting with CI/CD tools with Bazel, then a lot of years around Kafka infrastructure and incorporating tools and practices for event-driven architecture for Wix, and more recently around our generalized microservices framework that we've developed at Wix for our internal usage. Other than that, I'm a big yoga enthusiast, and I've given talks in numerous tech conferences around backend infrastructure subjects, and also written a lot of blog posts on these topics. A few words about Wix. So Wix is a powerful website building platform. We were pioneers of using AI already back in 2016 for creating websites. And with the Wix platform, you can manage your online presence, but also manage your business online, from managing the schedule and bookings for your yoga studio to sophisticated tools like third-party dropshipping. And our goal and our aim is to have any size and kind of business, big or small, utilize the Wix platform, which means that we have really a huge customer base and ever-growing traffic and data requirements and needs that we need to handle in order to have great performance. So a few numbers that you can visualize the scaling challenges. We process around 3.5 billion daily HTTP business transactions, and around 70 billion Kafka messages around these business events. And in terms of our transaction databases, we have roughly 4 petabytes of data, and that's completely not including all the analytical side of things. So our systems need to be able to grow in order to meet this amount of scale which keeps on growing, this amount of traffic and data. So how do we do that? Well, when you encounter scaling challenges, you have basically 2 options. You either vertically scale or horizontally scale. With vertical scale, you basically just increase the power of your machine. You add more compute resources, more memory resources. Usually it will mean to go to your cloud provider and change the type of your machine to something, well, more expensive. And with horizontal scaling, you actually increase the amount of machines or amount of nodes in a cluster, usually, in order to better handle the growing scale. Now, in terms of vertical scaling, here you can see a real graph that indicates a production incident that we had a few weeks ago, where it's a service that utilizes Redis, and it hit 100% CPU utilization, our Redis node. And it's not the first time that we hit the CPU threshold, so we already increased the machine sizes and added the CPU power. But again, this time, a new tenant was brought into the service and really increased the amount of traffic it got, so this happened. So while we can keep increasing the power that we add here for the CPU processing power, at some point, we won't be able to add any more, we'll reach the limit, and it will be very, very expensive. So each time something like this happens, you get a bottleneck, you need to address it. So yeah, vertical scaling definitely has its limits. But thankfully, we have horizontal scaling that can really help us. And theoretically, with horizontal scaling, you can get to almost infinite amount of resources that you need. So this talk is going to focus mainly on horizontal scaling and the strategies that we employed at Wix. With horizontal scaling, the idea is very simple. You distribute the workload among more nodes and more machines. And the idea is that by distributing this and distributing traffic and data, you hope to gain an overall improvement in performance. And when you think about it, basically there are two important dimensions to look at when you look at horizontal scaling. So one of them will be which application layer are you trying to scale? So we have web request balancing. So you have incoming web traffic, HTTP traffic. So you want to increase, get more nodes in and allow to balance the traffic between them with load balancers usually. And also when you have incoming events, you would like to balance between different consumers of these events for your message broker. It could be Kafka, it could be other messaging brokers as well. And of course, also for databases, you want to employ data sharding strategies. With sharding, it basically means you're going to split up your data into smaller shards. It could be more nodes, each dedicated to its own segment of the data set. But there is another dimension to look at when you're doing the horizontal scaling, and that is the routing or sharding strategy, which is what is the key space that we're going to choose for all these routes and shards. And basically, our goal is to have a key that is chosen, that it will allow us to have uniform distribution and will map us to the correct shard or node in a consistent manner. So you can start off with a very simple concept where you just divide the key space in a predetermined fixed way. Just divide it to 1, 2, and 3, and that's it. For instance, in our case, we have situations where we divide the key space based on the existing Kafka clusters that we have. But as you go along the spectrum, you try to get to a more, you will probably need to have more dynamism and a more dynamic way to employ strategies. And you'll usually use, at the end of the spectrum, a generalized hash functions where you try to map the incoming keys into the target space in a uniform way and a consistent manner. So in this talk, I'm going to present 5 unique strategies that Wix has employed and on this spectrum of key space selection. And I'm going to do it while showing different kinds of use cases, so you will have a clearer picture of why each strategy was chosen in order to handle this specific use case. So let's start with an example for fixed routing, and it's on the Kafka application layer. Many years I've worked on Kafka infrastructures, so some of the examples will definitely be in the Kafka world. And specifically, we're talking about using Kafka cluster tenancy. So a while back, we decided that we have to cut back on the cost of our managed Kafka solution. And we decided we can do that by deploying our own Kafka consumer proxy. And its job is to have smallest footprint of actually consuming from Kafka, because you need to pay for each event that you're consuming on. And have that proxy then relay the events to the Wix applications and microservices via RPC. But you may be noticing a problem here is that if we have a single Kafka consumer proxy cluster, then it may be really hard to balance all of the 70 billion events that need to go to a myriad of different use cases at Wix for all kinds of things. So we can get easily to a situation where we have a single point of failure. And if this proxy goes down, well, Wix cannot process any events at all. So that's a terrible thing. or it's fine. So with our idea here is very simple. We can just split up the consumer proxy code-based deployments into different fleets, one for each Kafka cluster. And in this way, when there is some issue with one of the Kafka clusters or with one of the specific fleets, then it doesn't mean that Wix cannot consume Kafka events anymore. It will just mean that some apps will get degraded performance because they care about this cluster, while other apps won't notice anything at all because they only consume from a Kafka cluster that has no issue or a fleet that has no issue. Cool, so that was just a way for me to show you that you really don't need to be like super complex in your decisions on how to partition a space or decide on how to partition the key space, right? And another very simple example, at least at the beginning with fixed routing, is how we decided to split up the key space according to quality of service. So this use case is actually about another infrastructure service that translates these Kafka events to HTTP webhooks in order for them to be consumed by external apps that are created on top of the Wix platform. Like I mentioned, it's a very complex platform. So imagine that we have two different applications. One of them is the restaurant orders application, and it needs to get events on incoming orders. And the other app has a URL called slowresponding.com. Weird URL, but maybe it hints at some issue that we have here. And of course, we are consuming from Kafka, which means that there could be situations where some applications will be put in, the incoming events will be part of the same queue. And then we have a situation here where a slow responding HTTP webhook will actually interfere with the processing time for restaurant orders. So while we do like the concept of queues because they help us increase the parallelism level, because you can have a lot of different queues, and for each queue you can have ordering guarantees, which is really nice. But we have hungry customers that want their lunch as soon as possible, or their dinner, and we need to get these orders into the third-party application as quickly as possible. So again, here what we decided to do, at least initially, is to have different fleets of the service for different quality of service needs. So at the beginning, all the configured URLs can be placed to be charged by quality of service group 2. But then if we get some complaint or some hint, hey, look out, we have a big customer who is noticing some that their application that they created for the Wix platform is having really slow responses, and they're getting complaints from their users. So okay, no problem. We'll easily, but manually configure it to a different quality of service group, and no one will interfere with them, or they have a lot less noisy neighbors. And if we get an alert that we have some very slow and a URL that is really timing out all the time and it's causing a lot of issues, no problem there. The on-caller can just move it to the quality of service group 3. And so these abusers will all be at the same pool and not bother the other deployment with the major, with all the major tenants all residing together and not really interfering with one another. So the idea here is start small and have a chance. Maybe we can have the best quality of service that everyone needs by just having 3 different fleets, and that's it. Maybe 4, maybe 5, but not more than that. And it actually worked. And so we didn't go with dynamic routing from the top. With dynamic routing, what I mean is we can actually have all these quality of service fleets, different groups, have automatic assignment of the tenants, right? So let's say all the tenants start off with group number 1, and then if the response times with the appropriate metric that the service itself or a management service looks at says that, okay, you are above 200 milliseconds for more than 5 minutes, and I'm going to reassign you automatically to this fleet with quality of service group 2. And maybe the situation is keep getting worse, and they have a bug on their website, so their response time is now higher than 2 seconds for longer than 5 minutes. Okay, you're going to be automatically reassigned to group number 3 according to the matrix. And of course, if the situation improves, you can then automatically be reassigned back to group 2, to group 1, etc. So this can be really, really helpful, right? But actually, we haven't done that yet. We don't see the reason to do that yet, because we noticed that most of our webhook customers are fine with having a little bit more millisecond latency. And if once in a while we get a complaint or we get an alert, okay, so we have the on-call, they can move it to the other place. If in the future we will see that it's getting more and more, it's happening more and more, then we can decide to do this complex complex technical logic in order to have this management automatic according to matrix. But for now, we save that trouble and hassle from us. Okay, and now we'll jump into 30,000 feet and actually look at the entire Wix level traffic, Wix web traffic, and see how we handled and balanced that. Well, in this case, again, Wix very early on chose a very simple strategy, surprisingly, on how to segment the key space to only 2. We have an editor segment and a public segment. So you may imagine by yourself, what does it mean to have an editor segment? Well, all the traffic that is related for site owners editing their site or managing their business will be on these types of segments in our data centers. And all traffic that's related to a visitor to a site that needs to get the site rendered as quickly as possible will go to the public segment. Now, the idea of splitting it is pretty straightforward. We want sites to be rendered as quickly as possible. And if there's some issue with the editor segment, we really don't want to affect the SLA of the public segment. So with this very simple binary split, we gain a lot more availability for our rendering segment. And it's doesn't mean that the editor segment has low availability. It just means that you have no interference between them, and you try to be as good as possible in both. So behind the scenes, we have our load balancers, including Nginx, which routes between both segments. And here, the key space is actually more dynamic because we route according to a specific key, which is the URL host. So if it's a wix.com site, it will go to the editor segment. But if it's a wixsite.com, which is a hosting site, then it will go to the public segment or the server rendering segment. And of course, for domains that Wix users purchase as custom domains, then of course also there are rules in place for them to be routed to the public segment. Cool. So we talked a bit about relatively simple and highly specialized situations. Now let's talk about more general purpose applications and microservices. So we're talking about dynamic routing of a high throughput reactions application. So what is this reaction application? Basically, it's a simple service that Wix has, for users to be able to like or unlike posts or post a custom emoji as a reaction. And we have a lot of different applications on the Wix platform that need the services of this app. We have an image gallery where you can like and comment and react on an image, or a blog app with a blog post, forum comments, etc. So we all really love to get more and more likes for what we post on social media, and it's quite natural for me as well. So what do we need to do for reactions application? This is a high throughput application because we get a lot of reactions in. I think last time I checked it was 1K RPM for write and 30,000 RPM for read, because a lot more you need a lot more reading of these reactions. So you need to handle high throughput, and then it has to be low latency reads, because we want, when the blog post is loaded, we want it to show the reactions quite quickly. And it has to be scalable, because the Wix traffic keeps growing over time, and this traffic is bound to increase dramatically. So how do we address these requirements? At least for the processing part, where we get an incoming web request for a new reaction, then we can definitely utilize Kafka, the very basic nature of Kafka topic partitions for balancing the traffic and the processing. Because Kafka allows to have great performance, it writes a new message really, really quickly to the persistence layer, and offers us great durability, and of course parallel processing between the different topic partitions and the order guarantees. And of course you can easily scale. Just a quick refresher, so Kafka has different, you can produce different topics, and these have different partitions. And in order to scale the amount of produce and consume from a topic, you just increase the amount of partitions, and then you can just increase the scale easily, and you add more consumers. So in this case, we have a parallelism level of 4. So let's say reactions applications has 4 pods in Kubernetes, and it can consume in parallel from 4 partitions. Of course, we can add more partitions, and each pod will process from more partitions. From each partition, you usually process sequentially, but at Wix, we're introducing a way to process sequentially for each specific key. So when the reaction application, you produce, according to some user, the key, then that will be processed sequentially, because you need to make sure that you have the ordering for a specific user. But other users that are on other keys will be processed in parallel. But how we do that is the topic of another talk. Okay, so we are processing the incoming requests for reactions very, very quickly. But we handled the traffic aspect of it. What about the data persistence layer? I mean, even if Kafka is really, really quick in distributing and fanning out the work, it doesn't mean that it will be fast enough. If the database will be very slow, then the overall performance will be majorly hit. We have as good performance only as the weakest link in our flow and layers. So let's talk about how we can make sure that the high throughput reaction application has good performance with the database. So that means that we need to employ good data sharding strategy. And for that, the reaction applications developers chose DynamoDB. So with DynamoDB, you get high throughput, large scale applications use cases, and it automatically partitions data across multiple nodes, and it really tries to do a good job in distributing the workloads evenly. It even automatically adjusts the partitions according to the traffic, and we'll see that in a bit. So just so everyone understands the basics with DynamoDB, you get a table for your specific data, and then you get a partition key and a sort key, and both of them will be the primary key for the item. which is kind of the key value. But the value here is more like document database, but it's schemaless, so each of the rows can have different typed attributes, which is a nice feature. So for the reactions application, they chose to have the partition key as a combination of the application and the item inside the application. So the application is an image gallery or forum and blog, etc. And the item is like which post in them it's part of. And then the sort key is according to user ID. And then the attributes basically is the list of reactions, quite simple. So behind the scenes, DynamoDB will take this information and split the items according to different partitions. And interestingly, each partition does have its limits on DynamoDB. It's not infinite scale, right? Each partition can have up to 10 gigabytes of data and 3,000 read capacity units, which roughly translates to 3,000 reads of 1 kilobyte per second, and 1,000 write capacity units, which roughly translates to 1,000 writes of 1 kilobyte per second. Now, what happens if the traffic or data exceeds these limits? Well, then DynamoDB will trigger a split of the partition into 2 partitions. And conversely, if the traffic really plummets for a long duration, it will consider to merge the 2 partitions back into a single partition in order to save on space and network resources. But if you get like a single item that is really in high demand, like a very popular blog post that keep getting reads on somewhere on the reactions, they will actually automatically move it to its own partition. So the partition will only have one single item because it needs all this very high network traffic capacity. And so I mentioned that they actually do dynamic partitioning with a simple hashing function. So DynamoDB, you chose the partition key, app plus item ID. No problem. They don't care what it is because they have a generic algorithm of hashing. They produce the hash key, which hopefully is consistent and has uniform distribution all along the key space, which is partitioned into separate partitions. And then the sort keys are just these items that share the partition key, sorted inside the partition for easy access when you query it. And if there is partition splitting, then it will just split it somewhere, but keep the order of the sorts in both partitions. Now, all of this is quite fun, so we looked a bit behind the scenes. But this is a managed service. So if you use it, you get this great auto-scaling out of the box, and you don't need to worry about it too much. But the higher the throughput you have for your application, the higher the cost. So you may end up in a situation with a very successful use case where you use DynamoDB, but it will become too expensive for you. So you need to be careful when using such a managed solution. Now, a more open source self-managed technology is for the following last strategy for dynamic routing, which is for the use case of data locality for enterprise customers. So Wix used to be like do-it-yourself website creation, but it's getting more and more big enterprise customers to create very complex sites. And these customers, as the bigger they are, the more regulation they have to adhere to, specifically, for instance, GDPR regulation. If anyone here ever had to implement GDPR regulation, I'm sure you remember it's a lot of fun. So specifically, we have to cater for data locality reasoning with regulation. We have here an example, a big enterprise customer, which is Wykert. It's a multinational company, and they decided to create on Wix an internal employee communication website. But they have both European employees and American employees, so they may have needed to actually have to adhere to regulation to have the European employees' information only be put in geographical data center inside Europe, and for Americans in the US data center. And these kinds of customers also need all this to be very configurable and easy to switch. So for that, Wix created new sets of segments and clusters for our databases inside our data centers. So if before this we only needed global database clusters that are replicated across can be replicated across all our data centers, now we also have dedicated geography-based clusters, specifically one in the US, like some in the US, and some only in the European Union. And specifically, most of our transaction data is put into MySQL. It's our power, it's like our main horse for doing all these things. And so it's self-deployed, self-managed. And there is a very crucial ingredient here that makes our global traffic routing and data routing possible with MySQL, which is ProxySQL. Without it, we would have been in a whole lot of trouble. So this is an open source library that basically load balances MySQL data traffic, and it really enhances high availability. Because if it notices that there is failure with some MySQL cluster, it automatically will route the traffic to the appropriate other data center, because we have active-passive architecture, which really saves our lives each time something like that happens. We don't need to get into panic mode. And also ProxySQL has very intelligent query routing abilities and sharding support. So here we see that our microservices, our backend artifacts, don't actually communicate directly with the MySQL clusters. They actually do it behind the ProxySQL cluster, which manages all of the connections for it, including read, write, read-only, and all of that logic. And I mentioned the sophisticated query rules, so we've configured ProxySQL to be aware of all these geo-sharded MySQL clusters. And then when we get to some website like Wykert that needs to get information only accessed in the European Union, then what we do is we actually put a hint into the SQL query or statement itself to hint that this query, because of this tenant, needs to go to US only, EU only, or it can go to a global cluster. And then ProxySQL will know how to route it automatically for us. So we don't only want to deal with data locality requirements, we actually want this to be a generic approach where we have very large MySQL databases which we have vertically scaled, which now cost more money, so we can shard them into smaller databases and do more horizontal scaling with the help of ProxySQL. And of course, also have dedicated database clusters, because a lot of enterprise customers prefer that. Okay, you're a SaaS provider, but I still want to have a dedicated cluster so I don't get any chance of a noisy neighbor affecting my business. And also supporting additional regional constraints. So all this can be supported by ProxySQL and these sophisticated query rules and query hints. Cool, so we went by all of these 5 strategies. So now for you, a summary of all the takeaways that you can take with you. The first one is horizontal scaling does increase complexity. Like I mostly talked about it, but if you can just start off with vertical scaling because it's cost effective, then do that. Otherwise, with horizontal scaling, you have a lot more complexity. The model and architecture of your system with all these different shards and nodes running about is harder to achieve. Especially during migrations, you want to migrate data. And now you need to consider the fact that the data is split around among a lot of different shards. You have one logical table in your code, but it's actually now scattered about, and you need to make sure that everything works correctly. And the overall mental complexity here is bigger for monitoring, for production investigations. So it's not a silver bullet. There is always a trade-off, and the trade-off here is complexity. Now, in terms of specific tech that we use, so of course, load balancers for web like Nginx are a crucial part of the Wix tech stack in order to make sure we have high availability for our rendering and for our editing segments. And Kafka is a major contributor to the stability and performance of our asynchronous processes, our event-driven processes, in order to scale them efficiently. And we have currently a managed solution. That's why we have more infrastructure on top to lower costs. But at the end of the day, the basic Kafka premise is very strong for scaling, of course. And then for certain use cases, we do employ DynamoDB because it offers a very easy setup of auto-scaling needs, auto-sharding of data. You don't even need to think about it. But because of the high cost, for most of the use cases, we actually use MySQL with SQL proxy, and that is cost-effective and allows us to handle the scaling that we require, including sharding between the different database nodes. So, how to split the key space? Well, you can choose maybe fixed segments because that will be easier. A small group of tenants means that you can just split according to clusters or according to the geography, US, EU, or according to quality of service or SLA, where one is very like zero latency, 9 nines, but others are less important so they can live separately. And of course, sometimes you need dynamic routing. Then you have the general case of the hash function, or more specialized predetermined knowledge of, you have more knowledge, so you can use a wildcard, a regex, straightforward, specific tenant mapping, where is each tenant going, and also ranges. I didn't talk about ranges in the talk, but you can split your key space into different ranges as well. So, to summarize everything I talked about into one slide, how do we approach our scaling needs and our requirements? So you start off with the degraded performance, right? We don't want to do premature optimization. And so now you know that your architecture is not good enough or there's some issue. So first of all, ask yourself, is the machine currently small enough and low cost enough that I can just increase its size and scale vertically? Go for it. Just add more compute and memory. But if you're in a situation where you're already paying quite a lot for the machines, then maybe consider doing horizontal scaling. And if you're doing horizontal scaling, you should ask yourself, can I divide the tenants into a small set of them? I just have small set. Great. Then use fixed sharding or routing and manually partition your deployments and data tables. But if you understand that you have too many tenants, then now the question that you need to ask yourself is, do I have knowledge about how to do this routing and sharding? How to do it with the predetermined knowledge? If the answer is yes, and you have these preset rules, then great, just use them to determine the shard, like the regex with wix.com or wixsite.com. But if you don't have this pre-knowledge, like a database like DynamoDB doesn't have any knowledge about your use case, then you just go with the hash. You do you use the hashing function. It will automatically distribute your requirements, your routes, your data uniformly in a consistent manner. And of course, you can also mix and match between fixed and dynamic in this case, like we have a fixed amount of segments, but we actually route between them in a dynamic manner. So yeah, when I researched this talk, I was really impressed with the amount of different technologies and different patterns that Wix employs just to make sure that traffic is properly handled. So I was impressed with that. I hope that you were impressed as well. And with that, I will open the floor to any questions if you have, and I would like to thank you very much for listening. And I put the slides on SlideShare, so you can just look up my name there, and you will find all the slides, including the takeaways at the end, so you can have them for later reference. Okay. Okay, so we have a question here. Quality of service splitting. Do we have good tools, libraries that can be used out of the box, or have to implement it on our own? Well, basically, you get, well, at Wix, we use Grafana. And when I mentioned the possibility to look for the response times of the different URLs, for the different URLs, it's basically a very simple metric that we can emit to Prometheus, and then you can automatically get the statistics from Prometheus, how long has some value, for which period this value is above certain threshold. So in that regard, I think it's almost out-of-the-box tool, but like you still need to fetch the data from, we use Grafana API a lot, and or other tooling to fetch the information from the time series database. I specifically am not aware of other tools, but maybe they're out there. So you can also approach me after the talk directly if you have any questions. You can also ask general questions about Wix backend infrastructure if you're interested about that, not only about scaling challenges, and about Kafka, about a lot of other topics you want. And let's see if there's any more questions. Okay, so I guess that's a wrap. Thank you very much for joining.